To the network seminar series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Professor Rohit Budhiraja. He will be speaking on AI ML based 6G wireless network design. Professor Rohit is currently a professor in IIT Kanpur, where he recently led an effort to design the first indigenous 5G network. This 5G technology has transferred to the industry. He is now leading an Indian government project from IIT Kanpur to design 5G plus / 6G standards. He also works closely with the industry, government organizations, and R&D labs to investigate 5G plus / 6G wireless technologies. He is currently a vice chairman of Bharat 6G Alliance and member of governing council of TSDSI, India's standard developed organization, and he has 25 years of experience in building 2G, 3G, 4G, and 5G wireless systems. His current research interest is to design 5G plus and 6G wireless networks by using machine learning and optimization based methods, and then investigate their performance by prototyping them. He has received CNR Rao Award from IIT Kanpur for architecting and designing the indigenous 5G network, IIT Kanpur Excellence in Teaching Award, Visvesvaraya Fellowship, and Early Career Research Award from the Government of India. The audience is encouraged to ask questions at any point during the talk. Questions can be asked either by unmuting or speaking directly or typing them in the chat box, from where they will be relayed to the speaker. Over to you, Professor.
Thank you, Srinivas, for the kind introduction, and I'm happy that you invited me and gave me an opportunity to talk about my work here. So I'll be talking about this AI/ML based 6G network design. And before that, I'll tell the audience where we are, what we have done with respect to 5G, and how is it going to evolve into 6G. I'll share my screen and then I'll start talking about it. So I hope my screen is visible to everyone.
Yes, sir.
Okay. So as Srinivas said, audience is free to ask me any questions during my talk, and then I can take up questions as and when they're asked, or after the talk as well. So this is the title of my talk, and as I said, basically I'll first be talking about what we have done with respect to the 5G network, and then we'll take it up from there. So what I'm showing you here is basically this the 5G radio network at IIT Kanpur. So if you look at basically any network, any wireless network, cellular network, so it has basically three main components. One is what the mobile, what you have in your hands, and the second part is basically the radio access network, which whose one part I'm showing you over here. So this is some device which you see on the tower, and this is the radio part using which the mobile connects to the external network. So this is basically the radio part, and then what it does is it receives the signals and or transmits the radio signals, digitizes them, and sends it to something called the baseband, which is the heart of a 5G network, and that's where all the signal processing happens. Okay, the complete signal processing happens in this, or 80% of that. Okay, so you see this device wherein the signal processing, all transmitter receiver algorithm run on this device. And the final part is this called the core network. Among other multiple other things, it basically authenticates users and then it does billing for them. So this is at this level, it does a lot of other things. So these are two main components other than the mobile. Okay, so what we have done is basically, I'll show you a demo of this, and you see what I'm showing you here is basically a commercial mobile being connected to our network. Okay, now this is what we have designed here along with another institutions. So this is the Samsung mobile which is connected to the network using which we have designed, which I showed you on the last slide. So now if you look at this, what goes inside these components, okay, I'm saying this is all what we have done from scratch. The entire hardware and the software was done within IIT Kanpur, there is IIT Madras and IIT Bombay. These three institutions came together and built the whole network. Okay, so so look at this. So this is basically the core network. It's basically the pure software, and it runs on these Dell servers. So no hardware component which we have built here, but the pure software is a massive software piece which runs on these servers. So this is one component. And then this is another component of this 5G network, which I mentioned. It is a baseband network. So if you rip it open, that's how it looks like. Okay. So this is what I'm showing you here. Okay. What it has is basically, if you look at this is a motherboard which you see in your PC, a similar motherboard. It's basically a server, and it's x86 process. Okay. And if I draw a software schematic of what is happening inside this, if you are aware of OSI model or TCP/IP model, there are basically 5 layers in any software, network software. Okay, so this is radio resource control, packet data convergence protocol, radio link control, MAC, medium access control layer. So all these layers run on this x86 server, which are there on this motherboard. Okay, as a communication engineer, what we might be interested in basically this physical layer, which is very time constrained. Okay, if you look at 5G, this is entire processing has to be finished in 0.5 millisecond. So this physical layer is basically run on these dedicated hardware, which you see over here, which was entirely designed at IIT Kanpur. Okay, so this is something like a PCI card which sits inside this server. You see this over here. Okay, so it's plugged into the motherboard. That's how we have designed it. Okay, so and it runs, as I said earlier, the complete physical layer, okay, of a 5G network. So this is what it is. Again, completely designed in-house, the entire hardware and the physical layer part. The higher layer part, basically we collaborated with the startup, and then that startup did these higher layers. Okay, but this is basically what was done here. Okay, and then this is the final radio part. This was done at a sister IIT Madras. So they did the hardware for this, and you look at this. What I'm showing you here, and it'll become very relevant in what we are talking about today, is this. It is basically a 16 antenna system. Okay, that's what this is what I'm showing you. So entire hardware was done here in these two institutions. Okay, so look at this. This is a 16 antenna system, 4x4. Okay, so that's the configuration I'm showing you here. Okay, and if again, so this is the antenna part, but a 16 antenna system, and if I open it, that's how it looks like. Okay, so you see here, these are basically the power supplies, and this is where again part of the physical layer is done, processing is done here. Okay, like the FFT and the pre-coding part, all this is done here. Okay, and then there are digital to analog converter, up converters, which are sitting here. Okay, so this is basically the physical layer part. Part of the physical layer is done here, and most of the physical layer, which I showed you, happens in the baseband unit. So both these devices are connected using an optical front haul, which has a 40 gigabit per second capacity. Okay, so you see this, that you send a signal, your mobile sends a signal, it is down converted here in this part, and then from there it is taken to the baseband unit over an optical front haul network. That's where you run all your basic physical layer algorithms. Okay, right. So, and including LDPC decoding, that's where it is done. So that's how a network is architected. Okay, and this technology, I showed you a demo initially, that it is working end to end. And we can connect using a commercial mobile. So this technology was a successful, we did a successful transfer of this technology. I'm showing you for one company here, we have done it for Tejas networks, and then we have transferred this technology to C-Dot as well. So that's where we were some time ago. This project started in 2018 and got over in 22. And after that, we have been enhancing it for various other features like making it for 32 antenna, improving the precoders, and then improving, like including other features which were not there initially. So this is the work which we have been doing for last 2-3 years. And the major piece of work which I'm going to talk about today is how we have been enhancing this network for AI/ML. I'll give you a brief picture of that. I'll be talking about one component of it, okay, which we have been focused on, and then I'll try to give you a brief glimpse of where we are. Okay, so this is the topic of today's talk: the role of AI/ML in 6G network. And even before we start talking about it, okay, I just wanted to talk about a brief history. So this is a 3G system which I designed in 2000. And if you look at it, okay, this had a single antenna system. This is, you look at this, this is an antenna port, and this was done in 2000. Very simple system, okay, for designed for 20 megahertz, okay, actually 2 megahertz. So then we moved on to this around 2010 and built a system which is 4G system, and it had 4 antennas. So you see that from 2000, from 3G, we moved from 1 antenna to 4 antennas in 2010. So this is a 4G system. And typically, all these deployments, 4G deployments, which you see all over the world, most of the time, they have basically 4 antennas. Even the 4G deployments here in India, they have four antennas maximum. Okay. Now, the point I'm trying to make over here is that from 1 antenna, we have moved on to 4 antennas from 3G to 4G. Now, from 4G to 5G, I showed you that we built a 16 antenna system. In fact, there's it's evolving to 32 antennas, but maximum of 64 antennas. That's the evolution. Okay, so from 4 to 64 antennas we have moved. Okay, from 4G to 5G. Okay, so you see this in every generation. The number of antenna is actually growing exponentially. Okay, and now what people are talking about in 2030, it will be something like this. Okay, that there will be these systems which will have antennas, which will have 512 antenna system. Okay, so we are talking about moving from 64 antenna to 512 antennas. Okay, and I'll tell you about the challenges which we face while designing the system and what role does AI play in that. Okay, so this is 512 antenna, and but why does this number of antenna keep increasing in every generation? Most of us understand, but I thought I'll talk about it briefly. Okay, that if you look at this as typical cellular deployment, okay, the way it works is there are these mobile phones which get connected to the base station. That's what I've shown you. Okay. Now each base station basically serves set as users in its cell, and cell is basically a coverage area. It's coverage area of the base station. Okay, so look at this base station. It'll have a coverage area of something like this. Okay, and what I mean by coverage area is basically the signal of this base station will be stronger in this part, okay, when compared with the signal of this base station. That's what typically coverage means. Okay, so you have a base station, it can serve users in this part of the cell. Okay, similarly, this base station, if you look at it, that it will basically serve users only in this cell. Okay, because beyond that, the signal of this base station will become stronger. Okay, that's the idea. Now, what happens to the users which are basically there on the cell boundary? Okay, right. So now see this, and another feature of this cellular network beyond 4G is that they use all these base stations typically reuse the entire frequency band in the spectrum in itself. Okay, let's say if it is Airtel, they have been given a chunk of 100 megahertz of spectrum. Okay, So this base station will be using 100 megahertz. The same 100 megahertz will be reused in this cell. Okay. Now, what is happening? Okay, the entire spectrum is being reused across all the cells. Okay, right, and what it naturally leads to is basically this interference. Okay, the inter-cell interference. Okay, and now, so what is happening over here? That this base station typically does not talk to this base station. Okay, and there is, if even if there is some interaction, it's a very loose interaction. Okay, in terms of the signaling, or in terms of when you do roaming, okay, when you roam from one base station to other, okay, it's basically that kind of interaction, but not the interaction at the physical layer level, wherein this base station can do some joint processing with this base station to reduce this interference. Okay, that doesn't happen. Okay, 4G, it was not happening. Even in 5G, it is not happening. Okay, so as a consequence of that, typically what is happening, that the transmission of this base station interferes with the transmission of this base station, and it leads to this something called intercell interference. So this is, I'm showing you about a 4G system wherein like it had 4 antennas and typically lead to this kind of interference. Now, what happened? Why did people move from 4 antennas in 4G to 16 or 64 antennas in 5G? What Margetta showed in 2010, that before that, even without these base stations talking to each other, okay, this, because you are using this large number of base station antennas, mobile still uses 1 or 2 antennas, maximum 4 antennas, okay, right? But it is a base station which uses, if you can deploy, that's a large number of antennas when compared with the number of antennas that the users. Okay, so what happens is that these base stations can form very sharp signals towards it, users. Okay, like you see this, when compared with 4G, these signals were interfering with each other, and now these signals are basically sharp signals, and they don't interfere with each other. There's no need for the base stations to talk to each other, and you can reduce this intercell interference. That was one of the main reasons that from 4G to 5G, we moved from 4 antennas to 64 antennas. One thing you have to keep in mind, I'm showing you these nice line of sight signals, but typically this is applicable in non-line of sight scenarios as well. Okay, so you can form a very sharp signal with these large number of antennas at the base station, and this helps you in reducing the interference. Okay, now from 16 or 64, now we are talking about 512 antennas at the base station. And what is happening over here is that another aspect comes into picture. Okay, that there is something called, like, you could multiplex users in the same time and frequency resource. Okay, and in the 5G system, you use something called spatial division multiple access, SDMA. Okay, so you use all these mobile stations are multiplexed on the same time and frequency resource. And typically, if there's a simple line of sight scenario, that these users, if you have to multiplex these users on the same time and frequency, they should not be aligned at the same angle to the base station. Okay, and they should form different angles to the base with the base station. Then only you can spatially multiplex them in a simple line of sight scenario. Okay, these conditions can be extended for non-line of sight systems as well, but just to understand. Okay, now what happens when you deploy these 512 number of antennas, or much larger number of antennas? Okay, then what happens is that the system enters something called the near field communication, because they increase the number of antennas. And instead of this, so what I'm showing you over here is this, basically the wave when it is received by the user equipment. So it looks like a spherical wave. And when you have the 16 or 64 antenna, the wave which is transmitted and received by the UE is actually a planar wave. Okay, but here it becomes a spherical wave when you deploy these large number of antennas, and the system enters this near field regime. Okay, so what people have shown, that instead of doing an SDMA, you could do something called LDMA. Okay, location division multiple access. Okay, so users located at same angle but at different distances can also be multiplexed on the same spectral resource. Okay, and this is what is called as LDMA. Okay, so you see this, that I can increase the number of users being multiplexed on the same spectral resource because I've entered something called near field regime. Okay, and the wavefronts have become spherical. So along with like reducing the intercell interference, I can serve a larger number of users. That's one of the main motivation for increasing these number of antennas, still from 5G to 6G. Okay, so and to summarize that, we have moved from one antenna to 512 antenna in the span of 20 to 30 years. Okay, but what are the challenges when you build these kind of large antenna MIMO systems? Okay, that's what I'm going to talk about, and that's where AI is going to play a key role. AI will play a big role in the design of overall system, but what I'm going to talk about is basically one application wherein which will enable us to design these large antenna system effectively. Okay, so this is basically a simple system model. Okay, I'm showing you a single antenna system as of now. Okay, so what is happening over here? The base station transmits a signal. Okay, it gets multiplied with this channel. Okay, y is equal to hx plus n. N is the noise which gets added at the receiver front end. Most of us are familiar with this model. Okay, now in order, so what, even before your receiver can estimate this x, or it has to estimate the channel. And when we talk about these large antenna systems, this channel knowledge, basically base station should also have this channel knowledge. Okay, I'll tell about this. Okay, why does it need? But the key point here is that who has the channel knowledge? Okay, it is the receiver which receives the signal. Okay, and which has this channel knowledge. It is easy for the receiver to estimate this channel H. Okay, because it has the received signal. Now, base station also needs to know this channel H. Okay, why does it need to know the channel H? Okay, this is basically, we spoke about this, right? That base station has large number of antennas. Okay, and it needs to align this signal towards its own receiver. Okay, now, but how does that happen? Base station needs the channel knowledge of this link. Okay, so that it can orient the signal like this. Okay, this is one of the key component that base station needs to have this channel knowledge to beamform its signals towards the mobile. Okay, now let's see this. Okay, in order to enable this, typically what is done here is that base station sends pilot signal X to the mobile. And what is the pilot signal? I'm sure most of us know, but it is something which is known to the receiver as well. Okay, this is the pilot signal which is known to the receiver. Okay, and let's say it is X is equal to 1. Okay, so receiver knows it. Now, when this pilot signal is transmitted, this is the received signal, y is equal to hx plus n, which is actually h plus n now. Now, this receiver, which is the UE in this case, user equipment, has this channel knowledge. Okay, it estimates the channel and sends it back to the base station. So look at this. What is happening? That this is a user which estimates the channel and sends it back to the base station. Keep this in mind. Okay, base station does not have the channel knowledge. Okay? This is the user which has the channel knowledge. It has to estimate the channel and send it back to the base station. Okay, so this is the complete feedback loop. Okay, so this is the base station sends the pilot signal, UE estimates the channel, and then sends it back to the base stations such that it can beamform the sharp signal towards its UE. Okay, so this is what has to be done even before the data gets transmitted to you. And this is required because base station has multiple antennas. You need to do this something called this sharp beamforming. It needs to do something called location division, multiple access, which we learned briefly in last few slides. Okay. Now, in order to enable this, so what is happening? Okay, now from one antenna system to, let's say, we move to two antenna system. Okay, now base station basically sends a single pilot signal, right? Okay, what happens? What kind of signal UE will receive? It will receive a signal like this: h1x plus h2x plus n. Okay, so y is equal to h1 plus h2 to x plus n. Okay, now look at this. So the mobile cannot estimate h1 and h2 separately. Okay, because what is it is receiving is the sum of these two signals, H1x plus H2x plus N. Okay, right? So it receives a single complex number, and from there it cannot basically estimate two complex number H1 and H2. Now, typically, what is done is here that base station sends orthogonal pilot signals, something like this. Okay, so from at the first instance, okay, it will send some x and 0. Okay, base station sends this orthogonal pilot signal x and 0. When I say x0, it is x and 0, basically switching off the second antenna. Okay, right? So the received signal the first time instant will be h1x, and this since this antenna is switched off, you don't get anything over here. Okay? Similarly, in the second time slot, a signal like this 0 and x is sent, and what UE will receive is y2, which is this plus h2. Okay. Now the point I'm trying to make here is that the signal something your receive system looks like this. Okay, y1, y2. Let's say it's over 2 time slots. This is your pilot signal, phi1, multiply this over here, and similarly you multiply this, you get a system looks like this. Now, what you have to notice here is that from when we are talking about one antenna system, it was only one pilot signal. Now, when we are talking about two antenna system, you need two pilots for the UE to estimate the channel. Okay. Now, that's how these pilots are sent in 5G system. Okay, that's where I'm showing you, that's how you receive your signal or data in a 5G mobile. Okay, what I'm showing you here is, this is one antenna. Okay, if it is a one antenna system, it is, you send only one antenna. If it is a two antenna system, you see this, you are basically using two resources. Okay, this is port here, we can understand it as a antenna. So if it is two antenna system, you need two resources to send orthogonal pilot signals, two orthogonal pilot signals. That's what we saw in the last slide. Okay. Now 6G system will deploy 512 antennas. That's what we understand in this presentation. Okay. Now what will happen? So our system model will look something like this. So what are we talking about? Okay. That now you'll have to transmit 512 signals, 512 pilot signals for the UE to estimate these different H1 to H512 channels. Okay, right? So look at this. Okay, I'll go back. Okay, so this is basically how you receive your signals. Okay, this is called a resource grid in a 5G system. So the overall number of resources, if you see in one resource, this is called a resource block. So it's a 12 subcarrier, and this is basically the time axis. So this physical resource block has 168 resources in itself. And now what we are talking about is using 512 of them for as pilot signals. It is a humongous overhead. Okay, right? So we need 512 orthogonal pilot signal, extremely high overhead. Now can we reduce? So what we are talking about here is, can we look at the properties of H and reduce the pilot overhead? And that's where I'll show you some use of machine learning. Okay. Now, and so what we said was, can we look at the properties of channel H to reduce this overhead? And now this is a channel H. Okay. Now what people have shown is that basically, if you look at this, if you look at the channel, okay, the way it is received by the user, the way it is observed by the user. Okay. So if you transform this channel to something called the angular domain, basically, if you take the IFFT of the signal of this channel, okay, the channel starts looking something like this. Okay, right? So this is that same 512 cross 1 vector which I showed you over here. Okay, all these elements are basically non-zero elements. Here, most of the elements, the elements in white are basically zeros. Okay, and what have I done here? I've just taken the IFFT of this H. Okay, and now using this, the channel starts looking to be sparse. Okay, there's a sparse channel, and then most of the entries are zero. Okay, right? And something what I'm doing over here is, I've taken only the discrete Fourier transform or inverse discrete Fourier transform, which is a non-transform matrix. Okay, I'm not doing anything specific to the channel. I'm just taking the IDFT. Okay, so the transform channel is sparse, and these non-zero entries, okay, basically have some structure. Basically, just for example, they are bunched together in this. Okay, right? And the strength degrees according to some given function, which is sync function typically. Okay, now what is our objective here? What we intend to do is use these properties, okay, to reduce the number of pilots which the base station is sending. Okay, now base station, that's the objective. Okay, that we want to transmit much lesser number of pilots than 512. Okay, now if you transmit this fewer number of pilots than 512, our system will look like this. Okay, that earlier when we were talking about 512 pilots, there were 512 observation over here. We were using 512 resources. Now what we intend to do over here is that, like, we want to use far fewer number of pilots than 512. Let's say in this example, I used only 50 pilots. Okay, so my matrix will become something like this. Okay, and what I have done here is, instead of, so I will use this whatever I saw here, I showed you here. Okay, h is equal to f h a. So what am I doing? I'll precode my pilots using this matrix f. And the point I made was that this matrix is known. It's a simple IDFT matrix. Okay, I precode my pilots using this precoder. And my overall channel, if you look at it, it becomes something like this. This is what I showed you. Now, we have 50 observations. Okay, the received signal dimension is 50 because I'm used only 50 pilots, 50 orthogonal pilots. Okay, and then, so what is happening over here is that I've compressed my system because I'm transmitting only 50 pilots. Okay, if I basically transmit 512 pilots, I have 512 variables, I have 512 equations, I can determine it easily. Okay, now if I want to transmit far fewer number of pilots, then I have to use the properties of the channel, and I see that I can use it because this channel is sparse. Okay, now, so this is typically what we have used. Okay, that is a Bayesian learning framework to estimate this channel. Okay, right, and this is one of this. Chandra uses it also in IIC. I have been also using this. Okay, the Bayesian learning framework to estimate this sparse channel H. Okay, how does this Bayesian learning framework work? You have a likelihood of this observation. Okay, then you have prior on this channel. Okay, and you are determining HA is the vector which you want to estimate. There is a posterior on the channel. Okay, so this is something what we do. Okay, so now here, if there's something called conjugation. Okay, if this likelihood is basically has a similar form as the prior, then that's what they're called as conjugate likelihood and prior pair. For example, like if the likelihood is Gaussian and the prior is Gaussian, okay, then it is easy to show that this posterior will also be Gaussian, and very easy to estimate this HA, okay, in this compressed system what we are talking about. Okay, but typically that doesn't happen. So these prior and the likelihood pairs are non-conjugate. They have a different form, functionally different form. Okay, so it's very difficult to determine the posterior or estimate the channel in that case. So what we essentially do there, we use these approximate inference techniques. Okay, they are called variational inference. So this is, I'll not go into these techniques in detail. This is the kind of work which we have been doing. Okay, so to estimate these channels using this probabilistic machine learning. Okay, now what we have also developed is basically these low complexity VI algorithms, variational inference algorithms. Basically, mobile has battery constraints. Can you develop these low complexity algorithms for mobile so that their battery does not run out very soon? So we have been doing that kind of work as well. And similar ideas could be used at the base station also. So basically designing these low complexity algorithms. Now where are we? Okay. So what we have done here is, look at this. Okay. What we have been able to do is that base station, even though it has 512 antennas, it is transmitting much lesser number of pilots than the number of antennas. And how are we able to do it? By exploiting the properties of the channel. Okay. Now, this mobile has been able to estimate the channel, but it has to be fed back. Now back to the base station. Okay, right? It has a channel. Now, how do you do that? Okay. So I'll show you what we have been doing. Okay, and this basically came from what is being discussed in the standardization body. Okay, that basically this is something on compression, what we are looking at. Okay, so I'll show you the example of this, that how this machine learning is being used in feeding this channel back to the base station. Okay, so what happens over here is, look at the first bullet. Okay, so what we are talking about is using these deep learning models to basically compress this information here. Okay, so the mobile estimates the channel, then it compresses this channel information. Okay, these are called something called autoencoder architectures. Okay, wherein base station compresses this channel, sends back this compressed information to the base station. Okay, and then base station uses that compressed channel to figure out what channel was estimated by the mobile station. Okay, that's the overall idea. Okay, now, so this is how typically it happens. At the mobile side, there is an encoder which compresses the channel which was estimated into a low dimensional code word. What is a low dimensional code word? Basically, look at this HA. Okay, it has this complex elements. Okay, now, so what are we doing over here? We compress this using a neural network. Okay, the encoder neural network which is sitting at the mobile side. Okay, now after receiving the code word, so this is the code word which is sent by the mobile to the base station. Now, after receiving the code word, base station reconstructs this HA using the decoder network. Okay, so this is something we call. Now, what is happening? So this is something called compression ratio. This is basically the size of S, which is the encoder, divided by 2NSNT. Okay, NS is this compression happens over the subcarriers and over the number of antennas. Okay, this is the kind of compression which we have been able to achieve. Okay, so you study this encoder and decoder architecture for different compression ratios. Okay, so that's what this number will become relevant in the subsequent slide, and that's why I'm introducing it over here. Now, the different architectures are being studied for this 6G standard. Okay, I'll give you examples of this. This is CSI-NET. These architectures have come out in last 3-4 years. Okay, this is basically convolutional neural network based architecture, CSI-NET. Transnet is basically the transformer based architecture, which is basically very powerful due to this chat GPT kind of tools. Okay, and then there is something what we have proposed is called CrossNet, cross attention based transformer. Okay, now, so what to just to recapture what is happening over here in this part of channel feedback loop, that UE has estimated the channel. It is trying to compress this channel now into a code word. Now, this code word is sent to the base station, and base station reconstructs this channel using another convolution, another network, another deep network. Okay, so this is basically, one is encoder network, other one is a decoder network. Okay, and as I said, there are these different architectures which are being studied, and I'll show you now. So this is our CrossNet architecture. I don't get carried away by a lot of information on this slide. What I want you to focus on this. Okay, so look at this. Okay, this is typically, if you look at the whole of it, there are multiple blocks in it. But what I want you to focus on this multi-head attention. Okay, and what I am showing you here is basically, this is the frequency domain data. This is angular domain data. Okay, so as I said, the compression happens over the frequency axis and on the antenna axis. Okay, now, so if you look at this, typically what people have been doing. Okay, so this basically handle this frequency domain and angular domain attention separately. Okay, now we realize that, okay, so there are certain these features which are common across this angular domain and frequency domain. Can we club them? Can we use attention across them? Okay, so the blocks over here, they are called self-attention. Okay, because they are focusing only on extracting the features in the frequency domain. This part, and this part is basically focusing on the angular domain. So what we did in this architecture which we proposed was basically use these cross attention blocks across this frequency and angular domain. Okay, frequency and angular domain, we use this cross attention blocks. Okay, that's what is our contribution. I mean, we started looking at it. In fact, that's where the standardization bodies also have been working actively on it. Okay, right. So there is this self attention block and there is this cross attention block. This is what we introduced. Now what is happening over here? You see this? Okay, so we are feeding this. There's a coupling across frequency and antenna domains. Okay, that's what we have done. Okay, so we take the information. This attention basically is taking information which is part of frequency domain. It is taking information from the angular domain. Similarly, by other way around, wherein this attention sitting over here in the angular domain is taking information from the frequency domain. Okay, so that's the modification we have done. It's a very simple modification. Okay, now using this, I show you something nice. Okay, now what I wanted to focus on this table is basically this. There are different kind of scenarios, inside and outside. Okay, indoors and outdoors. Okay, so these are different architectures, but look at this. So there are indoor scenarios, there are outdoor scenarios. Okay, what I'm showing you is the NMSE, normalized mean square error. Okay, so this is the error in the estimate. That's all. The normalized error in the estimate. Most of us understand this term. Okay, and what I'm showing you here is 1/4, 1/8, basically the compression ratio. The higher the compression ratio, I am basically compressing this channel more and more. Okay, while sending it back from the mobile to the base station. Okay, now look at this. Okay, that this is what we had proposed, and this is the state of the art. This is NMSE in terms of dB. So what we have been able to do is that -32 dB, that was the best which this architecture was giving, and we have been able to get -35 dB of NMSE. Okay, this is for one compression ratio. You compress the signal more, your NMSE increases. Okay, right? You see this. I'm talking about indoor scenarios. Okay, so for 1/4 compression was less, so the NMSE was -32 dB. The same architecture gives -22.36 dB. Similarly, it happens for us as well. Okay, that we have increased our NMSE from -34.5 to -24. But what is happening over here is that by using this cross attention, we have been able to basically reduce the NMSE. And in fact, we did it smartly. And look at these. These are common metrics or numbers to compare. How much is the parameter count? How much is the flop count? Okay, and so our architecture basically has a much lower complexity than these existing architectures as well. Okay, we are around 1.959 million flops, 3.12 million flops, and 1.59 parameters. So we have been able to do that as well. Okay, right. So this is the performance. Now one could ask this question that, okay, how much gain this crossnet attention is giving? Okay, so what we said was, okay, let's basically remove this something called ablation study. And what we did was that we removed this cross attention block. When I'm writing over here, crossnet light is basically without this cross attention blocks. Okay, right? So look at this. Now, when we reduce this cross attention block, okay, our NMSE increases from -34.5 to -27.4. Massive increase. Okay, right? So, and it's so that shows the importance of this cross attention blocks. Okay, that in fact, when we remove these cross attention blocks, you can see that our parameter and flop count actually reduces, but not that parameter is basically reduces marginally. The flop reduces considerably. But look at the reduction. Look at the increase in the NMSE. The NMSE degrades considerably. So that shows that this cross attention is basically able to extract the features across the domains, across frequency and antenna domain, and is able to improve the performance very well. Okay, so that's where the importance of this cross attention block. Okay, so what we have been able to do is that we have been able to use this machine learning, okay, in both the downlink channel estimation. Key thing was that basically the base station is transmitting much lesser number of pilots now. When it had to basically send 512 pilots, now it's sending, let's say, 1/10 of that. That's where first use of machine learning. Now the reverse use of machine learning in the reverse link basically is while compressing. And I'm showing you that by using smartly like transformers and some other people have used others as well. Okay, we are able to compress the signal and then also able to recover. Base station is able to recover the channel well by using this deep transformers or convolution neural network based architectures. So this is one use case. Okay, and before I wrap up, I just wanted to show you and take another 5 minutes that how we have been pushing this work in the standardization body. We started looking at this motivation of this deep learning architecture came from the standardization body because I and my team actually actively participate in this 5G plus 6G standardization. I just wanted to show you this is how we have been contributing. That's how 3GPP works. I'm sure some of you are familiar with it, but look at this. This is when we started working around 4 years, 3.5 years ago. Okay, so you have to attend all the meetings. Okay, the team has to travel, it has to attend all the meetings, and that's what we do. Okay, so from May 22, this was Corona time, so meetings were online, but slowly they became offline. Okay, so we have been attending all these meetings, and look at this. We have been pushing these ideas. Okay, that's where 2.5 years ago, 3GPP, which is the standardization body. Okay, and so they started looking at different use cases, and one such use case which we discussed in today's presentation is this channel information, state information compression. Okay, that's what we have been is being driven by us here from India. Okay, there are other institutions. We have been actively contributing to it, pushing these ideas into the standard. And what I'm showing you here is all these are the technical documents which we contribute in context of this. I work in other areas as well. In context of this presentation, I'm showing you, highlighting these our contributions with respect to this CSI compression, which channel state information compression. So you have to attend all these meetings. I'm showing you that this, look at this, where we were August 23, then ideas in February 24. You cannot really miss any of these meetings. Okay, so look at 27, 28, which is not highlighted. So these are the meetings which we keep attending. Look at this. All these meetings, all these technical documents are in context of basically the CSI compression. Okay, and through these technical documentations, you try to influence the discussion in the standardization body so that you could push your patents. You first patent these ideas, then push them into the standard. Okay, so this is where there are other meetings which we have also attended. I'm showing you till June 25. Okay, if you don't attend a meeting, your idea gets kicked out of the standardization body. But in context of this presentation, the problem which I discussed came out of this standardization, which was posed in the standardization. Okay, and we have been able to influence this standardization body to a reasonable degree. Okay, so I'll stop my presentation. Okay, I think I've been given 50 minutes. I'm reaching there. So here at IIT Kanpur, I've basically been looking at 3 different aspects of wireless systems. We perform this complete theoretical research, which I showed you. We use this variational inference kind of algorithms, all other probabilistic machine learning kind of algorithms to design nice signal processing algorithms. I showed you the way we push these ideas into the standards. Okay, the one example which I gave you was this, that about the CSI compression. Okay, then I've been building these systems for the last 25 years now. Okay, with this 5G system which we built, and now we are enhancing it for 6G. So this is the conclusion. Okay, I think this is a reference. Okay, this is the work which recently got accepted in IEEE wireless communication letter. This is the architecture which we had proposed, crossnet based architecture. Okay, and this is the conclusion. And we discussed this AI/ML based channel estimation. Now, this deep learning and the machine learning is being explored across all layers of 6G network. Okay, as I said, I mentioned this in the beginning that there are 5 layers in any wireless network. So how do you enhance the performance of these layers by using machine learning? Okay, and in this next year and a half, all these technologies will be studied. In fact, there was this meeting this week itself. My team was sitting there, okay, in Sweden. There was this, and they're coming back this week. And the standard will be drafted from 27 to 29. And you'll see this in 29 timeframe, 29-30 timeframe, this 6G network being developed and deployed. That's how it's a very exciting area time for a wireless engineer to be in, to developing these theoretical algorithms, to develop these standardize, to work in the standardization and then develop these systems as well. So thank you. This is what I had to tell you.
Thank you very much, Professor, for accepting our invitation and delivering such an insightful talk. Are there more questions from the audience? Sir, there is a question from the online. Sir, can you please
share my screen? Stop sharing my screen. Yeah, I can answer the question. Yeah, please.
Okay. Sir, can you please give more details about the inference time of the crossnet? Will it fall under the channel coherence time?
Okay, so yes, so I can get you those numbers. Okay, then how much is the basically this is the training time. I don't have this right up my sleeve, but it depends on, it's a function of, like, the channel inference time is a function of the GPUs you are using. Okay, and if you have a high-end GPU, okay, and then you can considerably reduce the coherence time. Okay, so I can get you those numbers, but readily they are not there up on my sleeve. But inference time is much lesser. That's what I can tell you. And just to tell you, it will fall within the coherence time. Okay, I don't have the number right there now.
Hello, Professor. Can you hear me?
Yeah. Praveen.
Yeah. So I have one question regarding, like, you have two setups. One is indoor and outdoor.
Yeah.
So why is CrossNet is performing worse in outdoor channel situations? Like, do you have any understanding on that?
Yeah.
Thank
We
you.
do have actually this question. We knew we have analyzed it. See, what is happening is I can share my screen, but let me do that. Okay. So what is happening over here is that, see, outdoor scenarios are much more complex than indoor scenarios. Okay, look at, that's why the NMSE gets increased over here. In the indoor scenarios, we are able to hit minus 32 dB, minus 35 dB. But look at outdoor scenarios. All these models start the performance start degrading because, first of all, the two reasons. One is outdoor scenario is much more complicated than indoor scenario because of many more reflections. Another thing is that the signal strength reduces, okay, because you can go multiple wavelength. The distance between the base station and UE can be much larger. Okay, which typically reduces the signal strength as well. Okay, so they are more complicated to learn. Now ours is a something called lightweight model. Okay, you look at this 2.2. This ILNet is also like somewhere close. All these lightweight models, they struggle, okay, when it comes to the outdoor scenarios. And that's where, because we have reduced the flop count and the parameter complex number of parameters also, so it is struggling to match the other methods. And because it's a lighter weight model, that's all. In fact, I have not shown you, we have basically done evaluation study, that there are other versions of it, now that we have asked this question, wherein our CrossNet performs better than these existing models. The flop count and parameter complexity is slightly higher. Okay, so it's a game between the complexity and of the model and complexity of the operating environment.
Yeah. Thank you, Professor.
Professor, I guess you have answered almost all the questions here. So thank you, everyone. Once again, thank you, Professor, for delivering such an interesting talk. And thank you all audience for attending and have a great evening.
Thank you. Thank you for inviting me. Thank you. I leave then. Thank you. Okay.